it a day. So my goal is to continue the discussion, the demonstration of ANSYS. In the previous tutorial, I had merely showed an example problem to show how the flow of information occurs in ANSYS to ultimately tell us what the temperature distribution in a typical body would look like. What I would like to do now is to solve a more realistic problem related to lithium-ion batteries. So what we will do is that we will build a 3D geometry of a battery pack containing two cells. Okay, containing two cells, and then we will start heating up those cells, and we want to understand how the temperature in the battery pack changes as a function of time. Okay, so towards that, let me start a new simulation. And let's create the geometry. We'll follow the same process. We'll create the geometry, we'll create a mesh, and then we will specify the properties, the heat generation rate, etc., ask it to solve it, and then we will look at our results. That's the standard process for any numerical simulation. Okay, this is taking a little bit of time. Let's allow it to do what it wants to do. Yeah, so this is the simulation that I did last time. I'm not touching it. I'm starting a new one, a brand new one, which is independent of it. Okay, actually this is not what I want, so let me get out of here and instead use design modeler, in which I will create my geometry. Let's just think of some good numbers here. These cells are 18650 cells, so the diameter of each cell is 18 millimeters. So the size of this battery pack could be 18 plus 18 plus 18, maybe about 50 millimeters or so. Okay, so I'm gonna go and change the units to millimeters, and I'm gonna start sketching first the base of my battery pack. Let me give it some dimensions. We agreed on 50 by 50. So I'll say 50 millimeters. Is this visible in the back? If not, please don't hesitate to come forward. Let me also align this with this. Good. Alright, so here is my 50 by 50 base. I'm going to extrude it. Hopefully this looks familiar from the work that we did yesterday. And the cells are 65 millimeters tall. Okay, so I will extrude it to 65 millimeters, and this is my base. This is my battery pack, right? I have to build two holes in it in order to insert my cells. So let's do that. For that, I would like to create a new plane first. From face, from this face, sure, and on plane 4, I will create a sketch for two circles. 18 and 18, yeah, and then I also want to sort of place them in the center. So this, I'll say distance between the center and this needs to be 25, and similarly the distance, will they fit? Yes, they should fit. This also needs to be 25. So I put them in the center. I also want to make sure that they're equally spaced. So this to this is, say, 5 millimeters. No, it needs to be 9, it needs to be more than 9, right? So let me call it 12 millimeters. So let's just do a simple asymmetry. This cell is very close to the boundary, and this cell we will push away from the boundary. I just want to be able to capture that effect here. So this versus this, from this distance is more than 12. It is, say, 18. You see what I'm saying? I'm trying to create a little bit of an asymmetry to see how it will affect my thermal performance. So let's go ahead and then take this sketch and create, extrude, slice material all the way to 65 millimeters, and I have now created my geometry that contains 3 solids. One is this base, correct? The second is this cell, and the third is that other cell. This cell, this cell, this cell, and the rest. Got it? Let me combine these into a single part, and I'm ready to move forward. Okay, I'm done with my geometry. Part A of the problem is done. I can always come back and change things around here, right? That's one of the advantages of numerical simulations. I can always come back. Somebody says, oh, can you push the cells closer to the boundary or away from the boundary, or can you change the size of the cells or the geometry or whatever? It's easy to come back here and make those changes. There is a small clearance between the two cells. At the top and bottom, no. Usually there is no clearance at the top and bottom.
Cell and the back bottom.
This clearance?
We are having the cuboid.
Yes.
And
I see what you're saying. No, typically the cells are very tightly packed in that clearance, and therefore it is very tight. So we'll ignore that for now. Okay. I know it's not going to be 0, and that effect can be accounted for if you really wish. For now, let's neglect that. Okay. All right. So I'm done with this here. I can close this, and I can go and mesh it. Last time I meshed it automatically. Today let me show you a few features of meshing, because the mesh last time was very unsatisfactory. It was too coarse. So let's open the meshing and have a little bit of control over how fine my mesh should be. So let's wait for the meshing to open. Usually meshing is the one that takes the most time. It takes a lot of time for the software to discretize the body into number of nodes and assign the locations of each node and so on. Okay. Oh, thank God. For a moment I thought it wasn't there. So what I can always do is start with generating the default mesh. The default mesh, as you can see, is not great. You know, the number of elements here, if I go down here and look, is only a few thousand, which is very, very poor. I can go up to 100,000 and it will still compute very quickly. So what I will do here is that I will change the default element size from 4e minus 3 to maybe 2e minus 3 and run this again. And you can see that my mesh has become better. I'll do this, I'll make it a little finer, and now it's taking time to mesh because the number of elements is now going up. Now I think I'm much happier with this mesh than I was with the previous mesh. Even this does not have a lot of elements. It has only 200,000 elements, which is okay. You know, I could go more. For the purposes of this demonstration, because I want to compute within a reasonable time, I will actually go back to 0.002. See, there is the trade-off between accuracy and computational cost. If I really wanted accuracy, I would have gone down even more. But because right now in this lecture, computational time is important for me, I want to demonstrate a lot of concepts in the limited time. So allow me to go coarser so that the calculations will happen a little faster. So let's live with this mesh, okay? All right. So I'll close here and I'm ready to, let me update the project so that I can go to the setup and start defining the materials and so on and so forth. There really is not much of a difference. Both of them solve roughly the same equations in roughly the same manner. So it all boils down to what you're more familiar with. I'm somehow more familiar with CFX. That's the only reason. In some way, in fact, Fluent is a more sophisticated, comprehensive tool. CFX is a little more basic. So what do we have to do here? We have to tell it what the materials are. We have to tell it what the boundary conditions are. We have to tell it how much heat is being generated in each cell, right? And since this is a transient simulation, we have to tell it how long to go in time in order to find the temperature field, okay? So let's remember to do each one of that when this new window opens. One by one, we will define the materials, the two materials, cell and pack. We will assign them to them. We will put a number for heat generation rate, the convective heat transfer coefficient, and I think that is about it. So to begin with, let me go to materials. Remember that this had only a few materials available. So I am going to insert a new material and I will call it cell or cell material, cell mat. I will tell that this is a solid and I will specify its properties. Its density is about 2200 kg per meter cube. These are based on my own understanding of these numbers. The thermal conductivity, we all know that the thermal conductivity of the cell is highly anisotropic. There is a way, by default it only accepts isotropic thermal conductivity. There is a hack around this GUI that you can use to specify anisotropic thermal conductivity, okay? Takes a little bit of time, so I'm not going to do that. Alright, so keep in mind that I'm doing a bit of an approximation in the interest of time. I will just assume the cell to have a single valued thermal conductivity of 0.5 watt per meter Kelvin, okay? And then I will define another material called pack mat, which is also a solid. The pack material is typically metal. It has higher density and thermal conductivity. So maybe we can assume values, that are representative of metals. The thermal conductivity will be higher. So let's assume a value of 10 watt per meter Kelvin or so. Steel different types of steels typically have thermal conductivity of that order. If it was aluminum, it would be even larger. Let me just for now assume values corresponding to steel. So let me OK out of here. Let me rename this as cell. So this cell is a solid and it is this and this. These two are cells. Okay? No, I will just select only one of them and I will assign it cell mat, and I will get out of here for a little bit. I want to rename this as cell 1. I want to define cell 1 and cell 2 separately. So this is cell 1. Let me similarly define cell 2. Which would be this one. It's a solid, it is cell mat, and then the third material here is the pack, which is the rest of it, and that is made up of pack mat. So I hope you can see that the software tool has been designed to be friendly to us, right? It's once you learn the basics of what is where, it's very easy to click and assign properties and do this, do that. There is no programming needed for this. There is no coding needed, right? Everything is nice and friendly. That is why it becomes easy for anybody to do numerical simulations. All right. So then there is going to be heat generation in this body. So I need to go to cell 1 and I need to insert a subdomain, and I'll call it cell 1 heat. And this is the entire cell itself, and in this there is a heat source, a total heat source of certain number of watts, right? So let's just say 50 watts of heat occurs here, or a better way of doing this is, I'll call it cell 1 heat gen, and I will define the meaning of cell 1 heat gen here. Cell 1 heat gen, this is equal to 50 watts. Okay? So it understands what the meaning of cell 1 heat gen is. Cell 1 heat gen is 50 watts. While I'm here, I can also define cell 2 heat gen, and that would also be, why not call it both 50 watts? 50 watts is a rather large number, I think, but we'll see what happens. Okay, so just like I defined cell 1 heat, let me insert a subdomain called cell 2 heat, and that would be all of this, and it would have a source called cell 2 heat gen. I'm continuously looking at this because if there's any error, spelling mistakes, etc., an error would pop up there. But so far I think everything is good. The last thing we need to do is to specify cooling. So in the pack material, I will insert a boundary. I will say the cooling boundary, which would be pretty much all the walls, 1, 2, 3, 4, 5, 6. On all of them, I will apply a heat transfer coefficient. I will call it H cool, and the outside temperature can be just 0 Kelvin. Again, remember I said last time, 0 Kelvin does not literally mean 0 Kelvin. When I say 0 Kelvin, I'm simply saying room temperature, ambient temperature, so that any other temperature that I find after my calculations are over is relative to ambient temperature. So if my simulation after all of this says that the temperature here is 10 Kelvin, it really means that the temperature there is 10 Kelvin above room temperature. Okay? Alright, so here we are. It threw up an error saying I don't know what H cool means, which is okay. I will define H cool to be 20 watt per meter square per Kelvin and oh good, it accepted it, so everything is good. We are ready to go. I do need to specify to the solver that I am interested in carrying out a transient simulation, and as soon as I say transient, it says how long do you want the simulation to run. So, and I will say how about we run it for 2000 seconds. Then it asks how many time steps do you want to take, what should be the time step, and here let me just choose 20 seconds time steps. So total of 100 time steps it will take, and initially the time is 0. Okay, and obviously if I am running a transient simulation, then I must specify the initial temperature. So the initial temperature everywhere is 0 Kelvin, room temperature. Okay, so I start with room temperature. These two cells will begin to generate heat, and I'm now going to understand how the temperature changes as a function of time. Under the solver control, just like last time, I'm going to tighten this a little bit, and I will also, inside this, I will say please save my results at each time step, and I will insert a temperature sensor inside. I will say expression, and I will say max val of temperature at cell 1. So this basically means please monitor the maximum value of temperature anywhere inside cell 1 and keep reporting it to me. Okay. And I can also define one more similarly. That would be monitor point 2. It would be max val of temperature at cell 2. If I wanted to place a temperature sensor at a specific location, I could do that too. Probe, exactly. I could place a probe anywhere I want and it would monitor the temperature there. But really I'm interested in the maximum temperature, and therefore I can define it this way. Okay, let's take a deep breath and make sure that we have defined everything we needed. Initial temperature has been defined. I think life is okay. The cell material and the properties were defined here, cell mat. Using what?
Using a blank material, and you are specifying.
I put in my own numbers. I inserted my own numbers, and as I was saying, there is an error here in the sense that for the cell material I'm specifying the thermal conductivity to be 0.5, whereas I know that it is anisotropic, right? There is a way to bypass this and specify anisotropic properties. Takes a little bit of time. You have to write a separate script for it. So let me skip that in the interest of time. Okay. All right, I think we are ready to go. By the way, the fact that you referred about the clearance between the cell and the pack, that there may be some contact resistance at that point, could be accounted for here. So by default, the solid to solid interface is defined based on perfect thermal contact between the two. But if you wish, you can come here and you can define a thermal contact resistance, or you can define that there is a thin material of air or epoxy of a certain thickness at that point. Okay, so if there is a contact resistance, it can be accounted for here. I'm not going to do that, and I'm just going to get out of here. Okay, any other questions or comments? The chemistry of the cell is not accounted for here explicitly. We have defined the heat generation rate to be 50 watts. So I am assuming that whatever chemistry is happening in the cell, I already know that it generates a constant 50 watts of heat. If the heat generation rate is a function of temperature, then I can model that as well. Okay, let me run this case first and let's look at the results. Then we will come back and change this 50 watts to be a function of temperature. Okay, then if we change it to a function of temperature, we will see the cell getting into thermal runaway under certain conditions. Okay, any other questions or comments? All right, so let's go out of here. And see, numerical simulations are easy in the sense that having set all this up, now you can start asking questions. What happens if the cell has a different diameter? What happens if the conductivity is different or the heat transfer coefficient is different? You can always come back here, change it and run your simulation again. Okay? And oftentimes if the geometry is complicated enough and if we are not able to derive an exact solution for it, like we have done for simple geometries, then numerical simulations is your only option. All right, so let's finish this here, and I'm ready to run this. I suspect that this simulation will also not take a long time to run, not more than a minute or so, perhaps even less. This is where it is setting up those equations, creating the matrix, doing the matrix inversion sometime now, and solving for temperature. These are my user points. The two cells have roughly the same temperature. One of them is slightly hotter because it was farther away from the heating boundary. You know, if it had been completely symmetric, these two curves would have been exactly identical to each other. And as you can see, it rises very fast to begin with and it slowly stabilizes. The temperature rises very high, right? The cell will not survive. 50 watts was too much of heat, I think. At this point, 200 degrees C temperature rise, the cell will blow up. So we already know, if somebody says, I want a cell that produces 50 watts of heating, not gonna work. Not possible. You probably have to increase the value of H, cool it more aggressively in order to bring down the temperature, right? Using this simulation framework, you can ask all these questions. What is the minimum H needed to be able to accommodate a 50 watt cell? Can I switch off one of the cells and only run one of them at a time? Will that help me reduce the temperature and so on? My heat generation rate was defined to be constant 50 watts. I can define it in other creative ways. I can say it is 50 watts for the first 30 seconds and then it goes down to 10 watts and then after 30 more seconds it comes up to 50 watts. So you're giving a small break to the cell in order to allow it to cool down a little bit, right? Will that allow you to keep the temperature within acceptable limits or not, right? You can even say if the cell temperature exceeds a certain value, shut it down completely for a certain amount of time, right? These are all strategies that you would probably use in real life and those can all be simulated in a setting like this. So we had specified 100 iterations, 100 steps, time steps. We are done with about 70 of them. So very soon it will finish up. Okay. And at that time it will say simulation done. We will be able to close this and open the results window. So let's look at the contour, all the domains, everywhere, and this is how the temperature field looks like at the final time. Okay, it's a little difficult to understand what in the world is going on here. So what I can do is to create a new location called a plane, a new plane location. This plane would be where is this plane? (65), half of 65 is 32.5, so 0.0325 should put us at the center. Does it? Yes. So on the contour I can go and say plot my temperature only in that plane, so that I can see a that's how the temperature looks like. This cell is slightly, not much, slightly cooler than the other one, simply because this is slightly closer to the cooling boundary. Not a big difference. So if your battery engineer asks you, should I place it this far or this far from the cooling boundary, your answer is yeah, doesn't matter, do whatever you want, right? It's not a major effect. Clearly your battery engineer is also juggling 5 other constraints, so he or she will be happy to hear you say it doesn't matter. Alright, I can also, by the way, look at this as a function of time. This is only the temperature at the final time. Initially everything is cold, of course, right? And then as time passes you can see the heat is being generated inside, and slowly it begins to diffuse outwards, and things get hotter and hotter as time passes. Right? You can literally see the wave traveling outwards as time passes. I think you can actually create an animation. Yeah, so this is how the temperature changes as a function of time. The temperature is rising, but it eventually reaches a steady state. I'm not worried, even though the temperature is very large, and we can fix that by changing the heat generation rate, it will not go to infinity. It will eventually stabilize. Okay, let's stop this here and let's go back, and as I had suggested, consider a scenario in which the heat generation rate becomes a function of temperature in one of the two cells. Meaning that one of the cells has gone rogue, and the heat generation in the cell will increase as a function of temperature. Let's see what will happen in a scenario like that. So I will say cell to heat gen. Let me just actually turn this into a very small number, and cell 1 heat generation, instead of 5 watts, I will say beta times temperature. Okay, it will not know what beta is, so I will insert beta. Okay, so it uses beta. Oops, it uses beta for something else. So let me sorry, I think pushed it too hard and moved it. Thank you. So I will rename it to, sorry, I will change this to and I will define this to, I need a value for beta. It should be a small number, I think. Let's just call it 2 watt per Kelvin. I hope that works. It does. So basically we are now saying that the heat generation rate is equal to 2 times the local temperature inside cell 1. Okay. In fact, I think this 2 number is extremely large. Let me make it 0.1 perhaps. Let's see. If thermal runaway doesn't happen, then we'll come back and increase this number. We'll kill the cell, I promise. One way or the other. Okay? All right. So in the interest of time, let me make my number of steps slightly larger. So instead of 20, I'll have 50. So that I have only 40 steps. Simulation will happen faster. Okay? Oh, and the initial temperature, let me make it slightly hotter. So this is initially about 20 Kelvin hotter than the ambient. So it is slightly warm to begin with, and let's see what happens as time passes. So this is ready to go, I think. I'm going to say clear generated data and just start from scratch. A user-friendly tool like this is actually almost addictive, right? Once you set it up, you can come up with all kinds of questions to ask. What if I do this? What if I do that? What if the cell thermal conductivity can change, or the cooling can change, or the material can change, or what have you? This should take 40 time steps. See, immediately you can see that the temperatures of the two cells are now very different. Cell 1 has a higher temperature, but it is not showing the going to infinity type of behavior yet. Will it? Will it not? I don't know. I think that beta number needs to 0.1 was too less, I think. So let's go back and push the cell a little more. Instead of 0.1 value for beta, let's make this 1. Yeah, I think that will kill the cell. Or maybe I should have made it 2. We'll see. Clear generated data. Alright, let's see what happens now. Yeah, see, that one took off right away. Earlier it was converging, now it is diverging. And even the innocent cell, which was really not generating much heat by itself, gets captured, gets caught in the crossfire, and it also undergoes thermal runaway. It's also doing the same thing, it's just doing it slower, right? You can see, it's not the actual numbers that is important. What is more important is the nature of the curve. Earlier it was like this, now it is like this. And the numbers you can see here are hopelessly large. See how sensitive that beta was. We made it from 0.1 to 1, and somewhere in between is the threshold beyond which this behavior happens. If you have the time, you can try it a few different values and you can get closer to the value at which this transition occurs. It is somewhere between 0.1 and 1.0. You know what I'm saying? I just want to let this finish so that we can look at the results and visualize what is going on as well. Once it gets caught in this positive feedback, there is no going back, right? That's sort of the beauty of this thing. More heat generation, more temperature rise, therefore more heat generation, therefore more temperature rise, and it's like a chakravyuh that it cannot get out of. It's doomed to fail. And not only did the first cell fail, but the second one also failed as a result of that. It failed a little later, and it failed a little less spectacularly, but nevertheless it failed, right? Let's go to the results window and see how this would look like in terms of the temperature field in the body. Any questions while this loads? The capabilities enabled by the simulation tools like CFX really make it possible for all of us to become creative. At the end of the day, the kind of math that I have presented has its own limitations. It can only work for certain specific simplified problems, right? You go out in the real world and try to solve real world problems. those mathematical results can guide your direction to go, right? But the exact analysis will probably boil down to numerical simulations like this. Okay? So let's open CF Exposed. Students like Mohammed Parisi from my lab, for example, did a lot of math in my lab. Now when he works for Tesla, I think he runs simulations all day. Okay, so I will see, one of the cells dies, the other one in which there was no heat generation. It's still very hot, by the way. It's not zero, it's extremely hot. In fact, let's run this as a video. To see how the temperature will change. For a long while, not much is happening. But towards the end, the whole thing explodes. This is a little difficult to understand because of the large temperature range. Even though it was blue for the most time, it was actually quite bad. You see what I'm saying? Let me see if I can. Will this help? It's very cold here. It remains cold. But the point is that it is still rising all the time. Sorry, I'm not able to capture the exact effect in order to visualize, but the time plot, yeah, this only shows up here because of the dramatic range. It only shows up in the end. But anyway, if you see the temperature curve, temperature versus time curve that we had shown, it was very clear that both of those cells are going to undergo thermal runaway. In fact, this is a very large range, right? If I was to reduce that range, you will already see that you saw that at early times, that it was sort of going there, and then at some point it just took off and the entire thing exploded. This is pretty much an explosion, right? It doesn't look very dramatic, but it is an explosion, and it is because of the large value of beta in our calculations. I can go and ask myself all kinds of questions now. What is the minimum value of beta at which this will not happen? How do I change the thermal conductivity? What happens if I change the packed material, right? The packed material had a thermal conductivity of only 10. What if it was 200? What if the cell had better thermal conductivity? And so on, right? Let's just run one more calculation at a somewhat better value of beta. We know that at 0.1 things were good, and at 1 things blew up. What number should we choose? I still wanted to blow up, but not as badly. 0.5? Yeah? Any other thoughts? We can only guess here, honestly. So, yeah, sure, 0.5. I have a feeling that it will still explode at 0.5. So, clear generated data. Yeah, run from initial conditions. And there you go. Our calculations have started. This is probably the last calculation we'll do today. Let's see how it works out. It tends to be going like this, but the green curve is going upwards, right? The red curve seems to want to reach a steady state, but at some point it will get the message and it will begin to curve up instead of going like this. See, at about this point, it has changed its shape from concave to convex, right? The evil brother has spoiled the good brother. Yeah, there's so much heat being generated in the other one that it's passing on some of its heat to the other, the good brother, and now they are both going to explode. Yep, it's done. It's gone. Even at 0.5, it goes. If you really want, we can try 0.2 and see how that looks. Why not? We'll just stop this. We know how it's going to look. Let's just go back and try. If this works. आपका magic. आप वो बोलते हैं ना, आपके हाथ में तो जादू है. Thank you. It just needs to last 2 more minutes, I think. So we will go back here. What number should we choose now? We've done 0.1, 1, 0.5, it fails. So, point what? 0.2, 0.3? How about 0.25? Okay, let's do 0.25. Any guesses on whether it will survive at 0.25 or not? How many of you say the good brother will survive? See, the thing is, we have proved this mathematically. Either both of them will survive or both of them will not survive. It cannot be that one of them survives, the other one doesn't survive, because the one that does not survive will eventually generate enough heat to kill the good one. So either they both survive or they both do not survive, and I am open to bets about what will happen in this case. Did I hit apply? Okay. All right, they both seem to be doing okay. Even the green one, but now it seems to be, the green one seems to be going the other way, the diverging way. Whereas the red one still wants to survive. The green one is clearly gone, and therefore eventually it will kill the red one as well. So far the red one is doing okay. This shows, the fact that it's taking a long time shows that we are very close to the threshold. At the threshold, add one more drop of beta and the thing explodes. So 0.25 is pretty darn close to the threshold. And you can see I can sort of feel now that it has changed shape. It was going concave and now it is starting to go convex. You give it a little more time and it will start rising rapidly as well. Well, we are at the end of the simulation time, so we could not quite see that. But I think it is quite clear that the green one is going to diverge, and ultimately, if you give it enough time, the red one will diverge as well. So the threshold is somewhere between 0.2 and 2.5. Point, yes, between 0.1 and 0.25. Okay. You give it a few more trials and you will get to, it's like the Newton-Raphson method, right? You're getting closer and closer to the root. Few more iterations, you will know exactly the threshold. And you know, honestly, come to think of it, finding the threshold in this manner is not easy, it is cumbersome. The mathematical tools that we have defined gave us a simple equation with which we could exactly derive the stability criteria. The only disadvantage there was that it was valid only for specific simple geometries. It cannot quite possibly do what we are doing here. Okay? Alright, so we are at 5 o'clock, so perhaps we can stop here. Thanks again for a good day. I'll see you all fresh and early tomorrow at 9 o'clock, and we'll talk about